Hey, once again, Marquis class, Flugum's class, and Olaf's class. This is our second unit on work, power, simple machines. This is lesson number 2, just after Mr. Flugum's introductory lesson. Just a quick review, what was covered in your introduction. Force, the units of force are newtons, and units for power are watts, units for work are joules. Just a quick practice, something that was covered first intro. This young lady's pushing on a car. If she were to exert a force of 125 newtons for, say, 10 meters, you'd go force times distance, and that's how you're going to determine how much work she did. So 125 times 10 equals 1,250 joules of work. Now, if she did that in 15 seconds and you wanted to know how much power that required, how many watts of power, you'd go 1,250 divided by 15 seconds. So the quicker she does that, the more power, the more watts that would take. If you put a lot of force into something, but it doesn't go anywhere, you have 0 joules of work because, force equals, work equals force times distance. And if your distance is 0, you're going to have 0 joules of work. The faster you do something, the more watts of power. So walking up a stadium stairs would be far less power than if you were to run, because you cut your amount of time down. So. Okay, now we're going to go into the stuff that I'm going to talk about, which is simple machines. The simple machines are devices that make work easier. There's a sacrifice, a give, but what you gain is less newtons required to do work. Simple machines fit into 2 main categories. One is levers, and the other one is inclined planes, the 2 kind of families of simple machines. The first one we're going to start talking about is levers, and you just see some examples of levers, some commonly used, some not so commonly used, but they're all examples of levers. The first type of levers can be broken down into 3 categories, and the first type is what's called a first-class lever, what I like to call a fulcrum sandwich. Fulcrum is the part of the lever that pivots, and anytime the fulcrum's in the middle, and the effort that you're putting into it on one side, the resistance, the thing that you're trying to pop or pry, that's on the opposite side of the fulcrum. That's a first-class lever. Here's some examples of first-class levers. A teeter-totter or seesaw, that's a first-class lever. And the hammer pulling the nail, the fulcrum's going to be in the middle. The effort's on one end, so that's going to be another example of a first-class lever. If you have a really super long effort arm, then you're going to have a big mechanical advantage. Mechanical advantage just used to describe how many newtons you have to put into something to make something happen. You don't have to put very many newtons of force into something if you have a big mechanical advantage. So having a long effort arm gives you a big mechanical advantage. So removing this bottle cap would require too many newtons of force, but when you use a first-class lever with a long effort arm, it comes right off. So that's an example. Okay, another class of lever is a second-class lever. First-class lever was a fulcrum sandwich. I'd say that the second-class lever is a resistance load sandwich. So all of your newtons of a resistance force is going to be in the middle. So as you can see with the guy with the wheelbarrow, he's got a big load of horse manure or whatever, and that the newtons of force of that horse manure are in between the fulcrum and the effort. So that's a second-class lever. Third-class lever, any type of weapon that you would swing, like a sword or an axe, is an example of a third-class lever. So when the effort force is in the middle, it's a third-class lever. Your resistance force is clear far at the end, and the fulcrum's right on one end. So in these examples, the fulcrum is at the very end of the machine. The effort force would be your wrist, and the resistance force would be the ball. There's other types of machine that would fit under the lever family too. Pulleys and wheels and axles. These guys have a fulcrum that pivots 360 degrees. It goes all the way around. And so because of that, you have a lever, just a lever that goes all the way around. They would fit into that same category, and they're used to gain a mechanical advantage. When you combine pulleys and wheels and axles and you combine them, you end up getting a huge mechanical advantage. So you might have 16 pulleys working along with a big diesel engine, and you can move things. You might have a mechanical advantage of 200. So when you apply a force of 5 newtons into it, 5 times 200, you end up with a really, really, really big mechanical advantage. And then on common, just everyday items that we use levers for. So a doorknob is a form of a lever, a wheel and axle, and a toothbrush, a pencil, and then the crank on that pencil sharpener. Okay, so the next kind of family of simple machines I'm going to talk about are the inclined planes, or what we might call the ramps. And with this, there's a give and a take. So the longer you have to go, the better your mechanical advantage is here. So he's having to go up a really, really long ramp, and the longer the ramp, the less effort, the less newtons he's going to have to put into getting that package up onto that truck. This is a form of mechanical advantage that's been used for ages. And if you look here, building the pyramids, they used slave labor to go up these really, really, really long ramps, getting a mechanical advantage to put big blocks up higher and higher. Also fitting into this family, so any type of wedge would be considered an inclined plane as well. So like the blade at the end of a knife, or a edge that you might use to hold open a door or split wood. So these are all just examples of inclined planes. A screw is just an inclined plane that's wrapped around a post. Same with spiral staircases, and ladders is a form of an inclined plane that's just steeper. The switchbacks that you might see on a hiking trail are also a form of inclined plane. Okay, so now we're going to ask you some questions that you're going to answer. You can go back through the beginning of the slide if you're having trouble answering these questions. And most of these questions I've categorized into an easy, medium, or challenging option. You can just pick which one you answer. Mr. Marquis and Mr. Flugum have a way that they would like you to turn theirs in with me. Just put your answers on a Google slide and share it with me. And I'll put it in the grade book. Okay. Question number 1. What's your name and what period do you have physical science? Also, if you could include your teacher's name, that helps us know who belongs to who when we're putting things in the grade book. Okay, question number 2. So you have 2 pictures here, one on the left, one on the right. Option 1 for question number 2, which one of these guys is doing work? And why is the other one not doing work? So one of these guys is doing actual work, the other one's not. Why? Option 2, what are the units for work? What are the units for power? It's option 2. Option 3, if Angry Samson pushes a marble pillar 2 meters with 1,000 newtons of force, how much work did he do? So that's your option number 2. You have to, or option number 3. You have to do a little bit of math on that. We can come back to that if I have time. Okay, question number 3. Like usual, has 3 options. Question number 3. Put these 4 simple machines into the correct category. So they're either inclined planes or levers. And where would they go? What category? Option number 2, explain what you give up when you use a spiral staircase in order to gain mechanical advantage. So there's a downside to a spiral staircase, but there's an upside. There's a mechanical advantage. It doesn't require as many newtons to get up to the 2nd story, but you do sacrifice something. Okay, option number 3, explain how you have to go a greater distance. I accidentally misspelled distance there. Explain how you have to go a greater distance in order to gain mechanical advantage. So with every simple machine, there's a give and a take. Okay, question number 4. What class lever are each of those? So, what class lever is the use of the screwdriver to open the paint lid? What class lever is oars being used to row a boat? And what class lever would a sword be as a weapon? Last question I'm going to ask. And again, you can just share these on a Google Doc with me. Mr. Marquis and Mr. Flugum have their way that they'd like you to submit these answers. Last question. In the case of both levers and inclined planes, you have to sacrifice something in order to gain a mechanical advantage. What is that something? Okay. Using these machines require fewer newtons of force to do work, but you have to invoke a greater something. Okay. I'm going to go back through those questions again real quickly. And please submit your responses. Question number 1, what's your name? And who's your teacher? And what period do you have physical science? Question number 2, one of these guys is doing work. Why is one not doing work? Option 2, what are the units for work? What are the units for power? And the last option, Samson pushes a marble pillar 2 meters with 1,000 newtons of force. How much work did he do? All right. Your next question. Put these 4 simple machines into the correct category. Would they fall under the category of inclined plane or lever? Option 2, explain what you give up when you use a spiral staircase in order to gain a mechanical advantage. And option 3, explain how you have to go a greater distance in order to gain a mechanical advantage. Question 4, what class lever would each of those be? This would be a first class lever, second class lever, third class lever. And your last question. In the case of both levers and inclined planes, you have to sacrifice something in order to gain a mechanical advantage. What is that something? Hope you guys are getting something out of these lessons. It's a lot different than having you in class and doing a pulley lab and a lever lab and an inclined plane lab and putting together something called a Rube Goldberg device, which is something we normally do. But anyway, at least you're able to touch bases with this stuff. If you go on to take physics your junior or senior year from Mr. Marquis, you'll revisit some of this stuff, and hopefully that'll be in school, and you'll be able to go into this stuff a little bit more in depth. But anyway, hope you guys are having a great April, and I'll see you when I do my next lesson. Thank you.